Okay, so let's get started. So today we will finish off the material on retransmission protocols and look into selective repeat, which we haven't talked much about yet, and then do an analysis of these stop and wait, go back in, and selective repeat in terms of their efficiency. And then move over to some small items, framing and flow control. And after that, we're done with that part of the course, the retransmission protocols, and we'll go on to the next topic, which is medium access control. But that's for the next lecture. So last week, we talked about go back N as a protocol. We have talked about stop and wait before that, but we did a little bit of go back N. And the idea with go back N is that we allow the transmitter to send several frames or packets, same thing. For the purpose of ARQ, we don't make a distinction between frames and packets. But anyways, so the idea with go back N is to allow the transmitter to send several packets in a row without waiting for acknowledgement, like stop and wait does. And to do that, we introduced this concept of a send window, which is a buffer that the transmitter has, in which it stores packets which have been transmitted but not yet acknowledged. And the size of that is important. It should be then large enough to hold enough packets such that we can transmit continuously without waiting for the buffer to clear or before we can transmit. So basically we want that to be large enough so we always can transmit when we have data, to avoid this idle medium, idle channel. So, and then we need a timeout also, and the timeout should be chosen as usual, bigger than the round trip time to avoid unnecessary retransmissions. So if we have a fixed frame duration TF and a fixed turnaround time T0, we pick the size of the transmit window to be T0 divided by TF. And this is typically not an integer, so we round that up. So this is rounding up these half square brackets or whatever you should call them. Okay, so then we have an integer here, and then we put the timeout to be equal to the send size, the size of the send window times TF. Now, when there are errors, we might want to increase this send size somewhat to be more robust against errors in lost acknowledgements, but this is typically not so important as it turns out. But anyways, we could have a bigger size window if we would like. So here A is some number greater than 0 in this case, integer. Okay, so let's go into selective repeat. So the basic idea here is similar to go back N. It's just now we use a buffer at the receiver side also. So we have a send window and we have a receive window. These are the two buffers. So the basic idea is that we at the receiver buffer out of order error-free received packets, because these are indeed error-free packets and they should be delivered at some point. But since they are out of order, they cannot be delivered at this time. But we store them at the receiver until we can deliver them. Okay. So many versions of this basic protocol exist, and we will present the one which is in the book as usual. So again, if you Google selective repeat or read about this on Wikipedia or some other source, some other book, you would find small variations of this basic protocol. But we'll stick to the one which is in the book. And in the book, these the acknowledgements are not cumulative, as we would see. So remember that the cumulative ACK means that if I get an acknowledgement that acknowledge the reception of one particular packet and all the previous packets to this one, that's called a cumulative ACK. Now here, ACKs are individual, so there is an ACK per packet. So an ACK only acknowledges one single packet. This is not necessary for selective repeat, but this is what's used in this protocol. And then also there is a single timer for this, which is not required either. One could have a timer per packet if one wants, and actually that's beneficial in some situations. But anyways, in the Furusan version, there is a single timer, and the idea is that when the timer expires, then we retransmit all outstanding packets. And remember, a packet is called outstanding if it has been sent but not yet acknowledged. Okay, so it's outstanding from the point of view of the transmitter. Okay, so basically it's like this, that we have a sender and a receiver, and there is an upper layer and then the ARQ protocol layer. So in this case, it happens to be the upper layer is the application layer and the lower layer is the transport layer. It doesn't need to be like that. It could. This ARQ protocol works at any level in the stack. But there is an upper layer and a lower layer. So the upper layer puts down some data that needs to be transmitted, which is encapsulated in a packet, which is transmitted over the channel. And then the receiver delivers this under certain circumstances and send acknowledgements back. And we go back and forth like this. So in a packet, we have the payload, and then we have a sequence number, and then also some type of checksum or CRC in order to check that this packet is valid. I perhaps didn't mention this, but the CRC could be on the entire packet or just the header of it. It depends a little bit. We have actually talked about this when the checksum is over the entire packet. So let's keep on talking like that. The acknowledgement that goes back has an ACNO in it, so that's some type of sequence number, and also a checksum such that when receiving an acknowledgement, one can check that no errors have occurred in the packet. And remember, error detection is not perfect, but we will assume perfect error detection for the purpose of discussing efficiency and so forth today. Okay, so we have now a send window. So this is the buffer at the sender side, and it has a certain size, and the size is the number of packets it can store. There are two pointers, two state variables here, one which is called SF, and that is pointing to the first outstanding packet. So what is that? Well, it's the oldest packet that's outstanding, that is, it has been transmitted, but it has not yet been acknowledged. And then there is a pointer which is pointing to the first empty spot in the send window. So here's where the next packet to send will be stored in this position, but at the moment it's empty. Okay. Now the new thing about this looks like go backend, but the new thing here now is that we can have packets inside here which have been acknowledged, but this out of order. Okay. So in this case, we have transmitted this packet, this packet, this packet, but we only received one acknowledgement, and that is for the middle packet at this point in time. The receiver also have now a window, which is called then the receive window. It has a certain size, and it has blank spots in it, and blank spots is where it has not yet received the packet, and then it has blue spots in it, is where packet has been received. And these blue packets are packets which are error-free, but they are not received in order. So these blue packets cannot be delivered up to the upper layer yet, because they're not in order. So these have to wait until we fill in the blank spots here. Okay. We have one state variable here, which is called Rn, which we can think of, this is the next packet to receive. It points at the first empty spot in the send window. Okay, so let's look into the send window a little bit more in detail. So first of all, we remember that sequence numbers are m-bit numbers, a finite number of bits. So if we have an m-bit sequence number, then the send window size and receive window size in the Furusan version of selected repeat have the same size, namely 2 to the power of m minus 1 or 2 to the m divided by 2. Okay, so if we have 4 bits, we have 8-bit. If we have 4 bits, then 2 to the 4 is 16, which means that we have 8 slots in the send window and 8 slots in the transmit window. Okay. Now, if an error-free acknowledgement arrives, it has an ACNO. Okay. The first thing we do is to check. Okay, we don't deal with errors. With acknowledgements that have errors in it, we throw them away. But if it's error-free, then we check ACNO. And then we check ACNO, and if it's less than SF, that is, if it's to the left here, we ignore it. Or if it's greater or equal to SN, which means that it's to the right here, it falls outside the window which contains the outstanding packets. And in that case, we just ignore it. Otherwise, we will mark the packet which has sequence number equal to the ACNO as acknowledgement. Okay? So the ACNO, if it's 8, for instance, then it acknowledges the packets with sequence number 8. So that will be acknowledging this packet. If it's 9, it acknowledges this packet. If it's 7, it acknowledges this packet, and so forth. Okay. Now, if ACNO is equal to SF, that is, we acknowledge the oldest outstanding packet, that's good news for us. Okay? Because that means that this packet has now been transmitted and delivered without errors. So therefore, we don't need to keep it anymore in memory. So with them, we can slide our window. And we slide the window, that is to adjust this SF to point at the oldest outstanding packet. So in this case, what happens if ACNO is equal to 7? What happens then? Oh. Exactly. So that means that this packet has now been delivered, and we move SF to point at the oldest outstanding packet, which in this case is 10. So we can slide multiple slots depending on the status of the send window. Right? Okay. Now, if SF is equal to SN, so we slide the whole, we empty the window, then of course we don't have any more outstanding packets. So if FS equal to SN, there are no more outstanding packets, and then we stop the timer. In other cases, when SF is less than SN, there is still an outstanding, at least one outstanding packet in the send window, and then we restart the timer. So we basically reset the timer and restart it. Okay. So that's how it works. And when the timer expires, then we retransmit all the outstanding packets. So if the timer expires at this point in time, before we have slided the window, we see that we have the 7 and 10 has not yet been acknowledged. So when the timer expires, we retransmit first 7 and then 10. Okay. But we leave 8 and 9, we don't retransmit 8 and 9 because we know these have already been delivered. Remember in go back N, when the timer expires, we retransmit everything which is in the send window. So that's a difference now. Any questions on this? Okay. So then continue then to look at the receive window. So here, when packets arrive, if there are errors, we just throw them away. When an error-free packet arrives with the sequence number SECNO, what do? Well, we check if SECNO is inside the receive window. Okay, and if it is, then we store the packet in the receive window, and we send an acknowledgement. And the acknowledgement has ACNO equal to SECNO, where SECNO is the sequence number of the packet that we just received. Okay, so the ACNO is equal to the sequence number of the packet which is error-free received. Okay, and if SECNO is equal to RN, then we slide the window. So what is RN? Well, remember that RN is pointing at the oldest packet not yet received. Okay, so in this case it's 7. So if we get a packet with ACNO with sequence number 7, that means that this packet has now been received. and therefore it's the older packet not yet received. So we just deliver that because we delivered 6 already, but now we can deliver 7, and we see we can deliver 8 and 9 again, and therefore we slide the window already all the way to 10 in this case. Okay, and then we wait for the next packet. When 10 arrives, we can slide the window to 12 and so forth. Okay, so if secno is equal to Rn, then we can slide the window, which means deliver all packets that are possible to deliver, that those packets that are in order, and then we just Rn, so Rn points to the oldest packet not yet received. Okay. If secno is outside the receive window, we simply discard it. Okay. Now in the book it said that we should send an ACK with ACNO Rn. This is actually a bug, so this we don't do. Okay, so remove this from the book, and then things will work. Okay, any questions on this? Okay, so now this is a selective repeat send window and receive window, and if we want to look at this as an example to see how this works, let's first of all take 3-bit sequence numbers. So this means that the size of the send window and receive window is 2 to the 3 divided by 2, which is 8 divided by 2, which is equal to 4. So equal size windows on the send and transmit size. So we see here that the send window have 4 slots in it. Here, and the receive window have also 4 slots in it. Okay. We initialize everything by putting okay, I thought I removed these things, so don't worry about the R's here. Okay, like this. Anyways, so we initialize SF and SN to 0, and we initialize RN to 0. So now we can start. So what happens then? Well, first we get a packet from the upper layer. We put that into the send window, and then we transmit that packet over the channel. If it's error-free, we put that into the receive window and immediately deliver that, so we can slide the window. So here now we have delivered packet number 0 has been delivered to the application. And then we send an acknowledgement 0 back, like this. This acknowledgement 0 allows us to slide the window to now point such that SF points to 1 and SN points to 1 too, because that's the window is empty now, and then we stop the timer. So this is a transaction that everything went well. So that's how it works now. Okay, now let's see when we have a few types of errors here. So we get the next packet from the application above. That's packet number 1. Packet number 1 is then put into the send window, and it's sent over the channel, and now it's lost. So of course nothing happens at the receiver side because the packet is lost. Then we get a new request from the application layer, from the layer above us, with packet number 2. Put packet number 2 in the send window, send that over the channel, and then we get an acknowledgement back. So in this case, it went error-free over the channel. So then it's put into the receive window. But since it's packet number 2 and we haven't received packet number 1 yet, we cannot deliver packet number 2 at this point. So, but packet 2 is put here for further use, right? And packet number 2 is acknowledged by sending it the acknowledgement back. And when the acknowledgement comes back here, we mark packet number 2 as being acknowledged in the send window. So at this point in time, the transmitter knows that it has transmitted 1 and 2. It knows that the receiver has received packet number 2. Okay. The receiver knows has packet number 2 stored here, but it's still waiting for packet number 1, which was actually lost up here. Okay. Now suppose we get a new packet here from the layer above, packet number 3. We put that into the send window. We transmit packet number 3, it arrives, but it's out of order, but we put that into the receive window, and we acknowledge number 3. And when we acknowledge number 3, the transmitter changes color from outstanding to received here. So 3, now the transmitter knows that 2 and 3 has been delivered, but 1 is still missing. We haven't gotten the acknowledgement of this. Actually, the transmitter doesn't really know whether the receiver has gotten this or not. The only thing it knows that he has transmitted it and has not yet seen an acknowledgement for it. So it's uncertain about the fate here. Okay, but then there is a timeout. And at that timeout, we retransmit all the packets which are outstanding in the send window. And in this case, it was only one packet, namely packet number 1. So we resend packet number 1, it goes over the channel. Now, since that means that we have now received packet number 1 in the send window, and we can deliver 1, 2, and 3. So we deliver 1, 2, and 3 in order to the layer above it, and we slide the whole window, and now it's empty again. And we send an acknowledgement back, and when the acknowledgement, if that arrives, then the transmitter say, okay, now 1 is received. So we mark that as received, and we know that 2 and 3 has been received, so we can slide the window all the way to 4. And then we're now synchronized again with empty send and transmit windows. So any questions on this logic? Okay. So okay, and also we stop the timer when we do this. So the thing is that we maintain a timer at the transmitter side, and when that expires, we transmit all packets which have not been acknowledged. And this eventually leads to the state where all these packets are indeed acknowledged, and we can move on to slide the window and so forth. Okay. There are a few typos for this graph in the book, but this one should be correct, at least when I scribbled out the red parts here. So that's a state variable which we actually don't need here. If we want to look at this in the finite state machine presentation instead, the transmitter sender has 2 states, the ready state and the blocking state. And the blocking state, we're in the blocking state when we are blocking the upper layer, which means we do that when our send window is full. We don't have any more space in it. Okay. So let's go through this. Okay. So we're in we start somewhere, and then we end up in the ready state. Now things can happen. We can get a request from the layer above it to send a packet. And if we do, we make a packet with the correct sequence number, we store a copy in the send window, and we send a packet, and we start a timer, and we increment the SN state variable. And then we go along this branch here, and then we check whether the window is full or not. If the window is full, then we go into the blocking state. If it's not full, we go back here. So if we get a lot of requests, we will loop around here until eventually we go down in the blocking state. Once we're in the blocking state, there are 2 things could happen. Either that we get a timeout, and if so, then we resend all outstanding packets in the window and reset the timer. We can also get an acknowledgement which is corrupt, and then we throw it away. And we can also get an error-free ACK that acknowledges one of the outstanding packets. And if that is the case, then we go from the blocking state here and see, can we slide the window? If we can slide the window, that means that we can empty up free space in it, and we go back to the ready state. If we cannot slide the window, we go back to the blocking state. But suppose we can slide it, and there is space now in send window, we go back into the ready state. And here again, if a packet arrives, then we mark it as received and slide the window if we can. If we get a corrupted ACK or an ACK about a packet which is not outstanding, then we just throw it away. So that's the sender. And the receiver, what does it do? Well, it starts and it's in the ready state. It's always in the ready state. And two things, a number of things can happen. We can get an error-free packet with the sequence number inside the window. Then if it's a duplicate, we just throw it away. Otherwise, we store it and we set an acknowledgement with ACNO equal to SECNO. SECNO is the sequence number of the packet we just received. If SECNO is equal to RN, that means that we can slide the window. So we deliver the packet and all consecutively, we basically slide the window as far as we can. And then we go back to the ready state. If we get a corrupt packet, we throw it away. And here's the change that you want to make a note of. That if we get an error-free packet with a sequence number outside the window boundaries, then we discard the packet, but we don't send an acknowledgement. So this is what Furusan says we should do. I think this is a mistake, because if we send an acknowledgement with an ACNO equal to RN, okay, RN is not the sequence number of the packet that we received, then if we do this, this will cause the transmitter to believe that the packet with SECNO RN has been received, which is not the case here. Okay, so that's a bug. Okay. So any questions on selective repeat here? Okay. So we have now talked about 3 protocols, retransmission protocols. The simplest we could think of, stop and wait. And then under certain circumstances, we saw that stop and wait is not so good. It mainly is not so good if the turnaround time is significant compared to the duration of the frame. That means that we spend a lot of time being idle at the transmitter. We send a packet and then we have to wait a long time before we get an acknowledgement until we can send the next packet. So to avoid that situation, we go to go back N. Go back N is such that we continuously transmit packets, and then so we transmit packets as fast as we can, and then wait for acknowledgements. Don't wait for acknowledgements before we send the next packet. So that improves things. And now we also saw that one problem with this is that in go back N, the received window is limited to have size 1, which means that it cannot store out of order packets, which is not good, right? So if we want to improve on that, we use selective repeat. Okay, so we have 3 now. We have 3 basic variants of ARQ. So the idea now is to go through them in a little bit more mathematical detail to see, what is the efficiency and data rate that they can provide. And then we figure out some design rules, basically, in what circumstances should we use one of these different protocols. So that's the idea now, okay? And we will base our analysis on the effective rate and the efficiency of the protocol. Okay. So we already actually did this a couple of lectures ago. We did the efficiency analysis for stop and wait. But just to refresh our minds what we're dealing with here, so let's consider definitions and so forth before we move on. So let's say that we're an ARQ protocol in layer N, and for simplicity or concreteness, just pick a layer here, maybe layer 3, say. Okay. Then the layer 3 service provides an error-free transmission of service data units, which is the packet data units from the layer above. Okay, so layer 4 PDUs. PDUs. This is what we should transmit. These are the packets we get from above, and these are equal to the layer 3 service data units. Okay. The effective data rate of the service, that is the data rate which is provided to layer 4. What is that? So layer 4, the layer above us, will see that we deliver data on its behalf with a certain rate. And this is what we call the effective rate. Okay. So how to calculate that? Well, it's basically a simple formula like this. We take the number of bits in the payload that we get from above, and then we divide through by the average time it takes to transmit this. Okay, so the layer above us will push down service data units to us with a certain number of bits, and these bits will, when I transmit push down the service data unit, it takes some time before this is delivered, and that is the transmission time. So we divide these two things with each other, and then we get an effective data rate. So if layer 2 in this case has an effective rate of R, then the efficiency of my layer, the ARQ layer, is the ratio between what I can deliver to the rate which I'm using. Okay? So if I'm the ARQ protocol, I have a rate below me, R bits per second, and then I deliver RF, the effective rate, upwards, and the ratio between these two things is how efficient I am. Okay? And this number is always less than 1. Okay. In pictures, it looks something like this. So the layer above us, say layer 4, and this is layer 3, and this is layer 2 for concreteness. So layer 4 is transmitting its protocol data units like this. Okay, so this is 4 PDU equal 3 SDU. Okay. So it transmits these packets virtually like this, back and forth, and the data rate it experiences is the effective bit rate, RF. Okay. Now, of course, these server data units goes down here. We get on a header, and then we transmit this like this, and we get the acknowledgements back. And the rate the rate we are experiencing is the rate that we get from layer below, which is R bits per second. Okay. Now, if we look into this service data unit, it consists of NF minus NO bits, and NO bits is the trailer and header, which is in the encapsulated service data unit on this layer. So we have some header bits and so forth, NO, O for overhead, and we have a total of NF bits in the frame. Out of these NF bits, NF minus NO are payload bits, these service data unit bits. Okay. And the acknowledgement also contains NA bits. Now, any questions on this? Okay. So then we did this a couple of weeks ago, or a couple of lectures ago. I can't recall exactly when, but the stop and wait efficiency and effective rate, we did this somewhat carefully. So this is from the transmitter and receiver. We have 2 timelines. So at this point in time, the transmitter initiates the first bit of the frame transmission, and then it goes over the channel, and it reaches the receiver after t-prop seconds, and then the full packet has been received at this point in time. Now the receiver then checks for errors and so forth. If there are no errors, then it transmits an acknowledgement back and starts to sending the acknowledgement here, and here it's received here and ends reception here. Then the sender inspects the acknowledgement, sequence numbers and so forth. It takes some processing time before everything is completed. So the time between when the first bit of the frame is transmitted until we're ready to transmit the next frame, this is known as the reaction time. This should be T0. It's T0, oops, sorry, what? T0. It is 2 times the processing time and propagation time plus TF, the frame duration, plus the duration of the acknowledgement. It's basically just add everything together here. So it then takes this amount of time to transmit 1 frame in the best of cases, so there are no errors here. So the effective rate when we have no errors is basically NF minus NO. Okay, that is the number of payload bits in the information frame divided by the time it takes to transmit that, which is T0 seconds. And if we calculate this out, we see that the efficiency is of this form. We won't go into the details here at this moment. What I want to do now is to relax the, what we want to do now is to say, okay, now suppose the frame or the acknowledgement is in error here. What happens then with the data rate? Okay, and the efficiency. And the answer is here, but let's derive it. Okay, so that's what we want to do now. Because the whole idea with retransmission protocols is to provide a reliable service for the layer above when the service below us is possibly unreliable. So of course we need to be able to handle errors. That's the whole idea. Okay, so let's talk about frame error or yeah. Okay, so let us introduce a random variable nt. Okay, nt is the number of times we need to transmit a particular frame before it's delivered correctly. Okay, so this is the number of transmissions needed before frame is delivered. Okay. So now, suppose the layer below me has a failure rate. Okay, there is a certain probability that if I give it a frame, it will lose it. Okay, and that error probability, let's call that PF. Suppose the probability of error is PF. That is the same thing to say that the probability of success is equal to 1 minus PF. Right? So I mean, if the probability of losing a frame is PF, the probability that it's not lost is 1 minus PF. Now, suppose frame errors occur independent of each other. Then nt, this random variable, so nt is the number of times I need to transmit a frame before it's delivered successfully. And that depends, of course, on how many errors that occur. If no errors occurs, then I only need one transmission. If the first one is in error, then I need more than one, and so forth. So then under the assumption that frame errors occur independently of each other, nt is a random variable that has a geometrical distribution. Have you heard about geometrical distributions before? No? Okay. But anyways, random variable with the geometric distribution. So what is that? Well, it's basically that the probability that nt is equal to some integer I. This is what we need to specify. Okay. So if nt is equal to I, what does that mean? Well, it means that we have transmitted I minus 1 frames, and all of these have been in error. and the ith frame that we transmit is correctly received. Okay. So, and the probability of a failure is PF. And if we take I minus 1 consecutive errors, then the probability of I minus 1 consecutive errors is PF to the power of IF. Sorry, PF to the power of I minus 1. And then the final packet, the IF packet, was received correctly. And that happens with probability 1 minus PF. Okay. So this is a geometrical distribution where this number is 1, 2, and so forth. There is no end to this. Okay. So NT is the number of transmission it takes before we deliver a packet. Okay. And if NT is equal to I, that means that I minus 1 of these transmissions were in error, and then one of the transmissions was correct. Is this pretty clear? Any questions about this? No. Okay. So then one can ask oneself, okay, so how many transmissions do I need to do on average? Well, let's calculate the expected value. So the expected value of n of t is a sum from 1 to infinity of the probability that nt is equal to I times I. Okay. So this is by definition the expected value of the random variable nt. And by just putting in this definition of what the probability that nt is equal to I into this, we can simply use it's just basic math, infinite series and so forth to get to the answer here. So I will spare you the details here, but it is what we expect it to be, namely 1 over 1 minus PF. Okay, and this is equal to 1 of the probability of success. Okay, and that makes perfect sense, right? Now, suppose the error probability is 10%. That means 1 out of 10 packets is in error. So, or do it like this. Say that the probability of success is 10%. Okay, how many times do I need to repeat this until I get a success on the average? Well, I need 10 times. So 1 over 0.1 is 10. Okay, so it makes perfect sense. If the success rate is 10%, the average number of times I need to do this to get a success is 10. Okay. Anyways, what we are actually looking for later on in our derivation is the expected of nt minus 1. Okay, and since we know the expected value of nt, we can simply compute this as the expected value of nt minus 1. And if we do that, we get this to be pf 1 minus pf. Simple algebra for this. Okay, so now we have these basic facts on the board to tell us a little bit on what is the probability of different events, how many transmissions we need, and the probabilities of this. So let's take 15 minutes and then continue to analyze the ARQ protocols after the break.